Hi everybody, I got the stream up a little bit late, so I'm gonna just let this run for 2 or 3 more minutes, give people a chance to get in here, and we'll get started shortly, so enjoy Mega Man 2. See you in a bit. Alright, that's probably long enough. Let me turn this down here. Welcome back to Chem 140. We're going to do our lecture that we should have done on Tuesday, today, so we're going to be starting Unit 9. What do we got on the agenda here? We've got lab number 3 is going to be due next Thursday. So we did the little let's go over the lab thing yesterday. Not really much to talk about, just more of an observations lab, although it's a different kind of observations. And the next quiz will be units 9 and 10, so you don't have to worry about that for the immediate future, I guess we'll say. And yeah, we're just playing Mega Man 2 music this week. There is video evidence online that I can finish Mega Man 2 in under 40 minutes. So if you can find that, it's out there. Oh, I gotta click over here first. What am I doing? I'm like advancing the slides and like, oh, that's not gonna work. Alright, what is Unit 9? Unit 9's about bonding. In this class so far, we've talked about very basic properties of matter, like what atoms are made of, and how we can categorize the stuff that they form. So, like, maybe they make mixtures, or maybe they make pure substances. But now what we're going to do is we're going to start looking at individual compounds. So, like, how does sodium chloride work? How does iron oxide work? Like, what are the features that hold atoms together in various types and states that we observe? So, like, ionic compound crystals versus molecular individual molecules and stuff like that. So that's the purpose of Units 9 and 10. Unit 9, we're going to talk about ions, and Unit 10, we're going to talk about covalent compounds. We're going to go over this in a lot more detail in 161, but for now, we'll just do the basics. Speaking of basics, I should probably get my tablet out. I forgot to do that. It just sits in a box over here, so let me put it... There we go. Alright, so, in any substance that has multiple atoms contained within it, those atoms are held together by a force called a bond. So a chemical bond is the attraction between any two atoms that holds them together and make a compound. Now, the attraction is generally focused between two atoms, but bonds can be, by their nature, attracting multiple atoms at once, or maybe only connecting two specific atoms, or whatever. There are various ways to define bonds, as we're going to see. But we're going to say, oh, there's something that holds these two things together. That thing is a bond, whatever it is. And we'll discuss that again as we go on. Now, all bonding occurs due to electrostatic forces and the attraction of positive and negative charges. Depending on where those charges are located and how they are used, we get a different type of bond. Now, because there's only one mobile charge carrier, which is the electron, most of this is going to involve putting electrons in certain places. Now, those certain places might be, oh, I'm going to stick them between these two atoms. Or they're going to be, oh, I'm going to just give away my electrons. Now, this thing has more electrons than it started with, and it's overall negative. I have fewer electrons, I'm overall positive. So, and then there are even other types of bonding for things like metals. So we're not going to talk about metallic bonding. We're going to only talk about these two types of bonding here on the screen. So the first one's ionic bonding. Ionic bonding requires you to transfer electrons from one atom to another. And so I like to think that this is like give and take. Some atoms have a propensity to give away their electrons. Other atoms have a propensity to keep them. They don't want them to be lost, but they'll take any extras they can find. And then other atoms don't know what to do with their electrons. They just kind of like, oh, I have so many options. Down here, we have covalent bonding. Covalent bonding involves sharing electrons. And so what's happening here in covalent bonding is that instead of just me giving away an electron and acquiring a charge in some way, electrons are instead pooled together in like a common sort of fund, I guess you could say, between atoms. And it's literally between the atoms. The electrons are placed in a region that is between the two atoms most of the time so that you can form an interaction. I'll draw that picture when we get to covalent bonding. Like I said before, Unit 9 is going to be ionic bonding. Unit 10 is going to be covalent bonding. Oops, that didn't work. There we go. All right. Now, we're not really going into much detail on electronic structure in this class. So if I show you this picture, keep in mind that this picture is not the whole story about how electrons are arranged around atoms, but it is a good starting point. The issue with this diagram is that it looks like my electrons, my electrons appear to be in what I would call orbits. And I'm going to put this caveat down here, but they're not. So for this model of an atom, what the diagram has done is it has counted electrons and then placed them on these rings. And those rings, it looks like, to someone interpreting this diagram with little chemistry background, because this is an introductory course, that's all of us, we would think, oh, okay, well, maybe the electrons are moving and they go around the rings, kind of like how planets go around the sun. And so that's an okay model for us to consider right now, but it's not actually what happens. But we're not really concerned about where the electrons are exactly. We care about where they are approximately for bonding. And so the analogy that we're going to make when we think about bonding is the following. Let's suppose I have two atoms down here. I'm just going to have just generic atom A and then generic atom B. And these two want to form a bond, so they will bonk into each other. Of the electrons that are shown, which electrons will be the ones that you think would engage in bonding? For example, let's look at bromine. Would these electrons in the middle of bromine be the ones responsible for bonding? If you're looking at it and going like, well, how the heck would we get to them? That's exactly right. We can't get to those electrons. They're buried in the middle, right? We'd have to tear through all these other electrons. So, can't be those in the middle. Could it be the ring that we have the most in? Well, there's still other electrons in the way, right? You probably see where I'm going with this. So, how do I get to these electrons? Well, I'd have to go through the ones on the outside first. And what do all electrons do to each other? Well, every electron has a negative charge. So this electron here is a negative charge, and so does this one, and this one, and this one, and this one, and this one. And they all repel each other. Because like charges repel, right? They're attracted to the nucleus, so they don't push each other out into the abyss where they wouldn't see the atom again. But they do push each other a lot, and so having electrons that are buried in the core doesn't really make much sense if we're going to try and use them for bonding. So the electrons that end up getting used in bonding are the outermost electrons. And we give those a special name. We're going to call them valence electrons. So what I'm going to do is I'm going to highlight all the valence electrons in light blue here. So valence electrons are the electrons on the outside. And that makes sense that we would use the outermost electrons for bonding, because if two entities bonk into each other, the outside electrons are the ones that are going to contact each other. The inside ones won't get that far because they're repelled further inside by the outer electrons, even though there are more of them. So regardless of how our electrons exist around the atom, and they're not in these constrained orbits, remember, that'll be important in 161. To some degree, there will always be some number of electrons on the outside on average. Those outer electrons are going to be our valence electrons. All right. So again, those are called valence electrons. Oops. Now, the inside electrons are called core electrons. Core electrons are essentially just there for bookkeeping. They neutralize the charge on the nucleus that is felt by the electrons on the outside. But as far as like chemistry is concerned, we don't really care very much about them, at least at this level. Later on, we will care about them to some extent. Like if you get to like 361, where we talk about inorganic chemistry and d orbitals and stuff like that. Like that's my degree. That's what I majored in. So I find all that's really interesting. But as a first year chemistry student, like you don't need to know any of that stuff. It's not important. Right now, the focus is the outermost electrons. Now, how many electrons are on the outside? That depends on what element you're looking at. So if we go to the periodic table, which I didn't pull up, actually. Let me go get P table out really quick. Oops. I hit O table, which apparently was closest to my bank account. Which is funny, because the first letter in my bank URL is not O, it's G. So, let's see here. Window capture. Periodic table. Let's see what that captures. That's not bad, I guess. Okay, so I definitely want these numbers in here to show the groups. Let me capture the size of the periodic table here. All right, so if we look at the periodic table, you'll see that each element falls into a group. And those groups are numbered right here, 1 through 18. For the elements that are in these two columns here, so the first two groups, 1 and 2, and then 13 through 18, the number of electrons that is on the outermost ring, the number of valence electrons, is going to be the ones digit in the group. So over here in this column, these elements are in group 2. The ones digit of the group is 2. There are 2 valence electrons in each of these elements. Over here, the ones digit is 4. So in this group, there would be 4 valence electrons. And this is true for every element in these groups, 1 and 2, and then 13 through 18, except helium. Helium's kind of weird. Helium just has 2 electrons, and that's it. Now, if you're using the A and B scheme for numbering groups, for example, hydrogen would be in group 1A, then you just use the group number, provided that the group is A. Let me go back here really quickly. You'll notice that I skipped over all the transition metals. The transition metals don't really follow these rules. We'll talk about special rules that they follow in Chem 161. So we're only going to look at what we're going to call main group elements. And yeah, fluorine would have 7 valence electrons, because it is in group 17 and the ones digit is the 7. On the screen here, I've only picked group 7A or group 17 elements, so they should all have 7 electrons on the outside. And so if I do this, 1, 2, 3, 4, 5, 6, 7, you'll notice that they do. So all elements in group 17 or 7A have 7 valence electrons. And this will always be true. That's going to be relevant to us because one of the things that we're going to be doing is counting valence electrons, okay? So this is the foundation of bonding, is you got to be able to count valence electrons, and you do that by looking at the group. All right, so hopefully you have a periodic table handy, or you have called up P table. What I want you to do is find phosphorus and tell me how many valence electrons it has and type it in the chat. And that shouldn't take you more than a minute, but I'll give you like a minute or two just to get periodic table up to use. So I'll see you in a bit. All right. What group is phosphorus in on the periodic table? While you write that in, Maya will meow at you. Meow. Say hi. Meow. Okay. Maya's been a pest this morning, but I think she's calmed down now. I'm just trying to pet her so that she stops meowing at me. What group is phosphorus in? According to your periodic table. Give you a hint. It's element 15. So that puts it in group 15. Very good. That's a coincidence, by the way, that it's element number 15 and also in group 15. But it's in group 15. The ones digit of its group number is 5, so it should have 5 valence electrons. All right. What is this valence shell that I've been mentioning here? If that was in the previous slides, I forgot to talk about that. The valence shell is how many of these electron rings we have around our nucleus. And that number corresponds to the period. So another way that you can think about doing this is, if I could click on the, there we go, is to think that the valence shell number is going to be the period, and the number of electrons is going to be the group number, or at least the ones digit. All right, let's do another example here, but notice that I'm going to change things up. I want you to tell me the valence shell and the number of electrons in O with a minus charge. Now, what the heck is this? What does this mean? Think about what that means and tell me how many valence electrons that should have. Start with how many valence electrons just regular old oxygen should have, and then try and make it minus. How would you do that? All right, so let's bring up the table here. Boop, there it is. I'm going to go find oxygen on it. Boop, there it is, right here. Oxygen's in group 16. The ones digit is 6, so it should have 6 valence electrons. But if you're going to make it negative, that means you're going to have to add extra electrons in there. 1 for each negative charge you want to acquire. So 6 plus 1 would be 7 valence electrons. So when you change the number of electrons with a species, you change the number of valence electrons that are present. And so we can do this all we want to. We can add or remove valence electrons all day. In fact, that's going to be the whole gimmick behind ionic bonding, is how do we get to this magic number 8? Because as you'll notice, the highest number of valence electrons you could possibly get on the periodic table is 8. That would be column 18, right? If I go to the next row, or the next element, I end up going all the way back down and all the way to the left, and I start a new valence shell. So this is how electrons are structured. You start putting in electrons, and then eventually you run out of space, and you have to start making a new valence shell. As the shells get further and further and further from the nucleus, there's more space to work with. Obviously, if you're really close and you have a small radius, you would have a small area for your electrons to go in. That's why the first row of the periodic table is so small. There's only 2 things here. That's all we have space for. The next few have space for 8. The next one has space for 18, and so on and so forth. And it gets bigger and bigger and bigger and bigger and bigger as you go. Now, that's the short version. It's a little more complicated than that because, well, why does it go 2, 8, 8, 18? It kind of doesn't. There's more to it than that. But for our purposes, that's a good enough analogy for now. All right. What if I do this with calcium? So let's look at calcium here. Find it on the periodic table. Tell me how many valence electrons it has, and then make it 2+. What do you got to do that? How many valence electrons will there be? Think carefully about your answer. Well, it's shell 4, but 4 valence electrons is not the right answer. I'll give you a hint. Technically speaking, 0 is correct, but it's not the best answer. Think about the diagram that we showed before with the electrons. I should probably remove the periodic table so you can see what the problem statement is. So it's calcium 2+ here. I don't know if I was muted when I said that. So 4th shell with 8 electrons is very close to the correct answer. Or the truest answer, I should say. But there is one error in there. Can you find it? There you go. That's the right answer. So 3rd shell and 8 electrons. Let's show how we got to that. So I need to put this on the screen, but I also need some space to draw here. All right. So let's draw calcium right here. I'm going to draw just the diagram for it. And so I'm going to put, here's shell 1, and then shell 2 would have some electrons around it. And then shell 3 would have some electrons around it. It's only going to have 8, but I didn't really space them out very well. And then shell 4 would have 2 electrons around it. So this would be my valence shell right here. So let's highlight that. Whoop. That didn't quite work because I can't see the cursor. There we go. There's my valence shell. Now what I'm going to do is I'm going to erase, boop, boop, 2 electrons to make it calcium plus 2, right? But now where's the valence shell? Well, there's nothing here, so it can't be a valence shell, right? So now the new valence shell is the previous layer. And so that would be valence shell 3 with 8 valence electrons. All right. Now, for our purposes, do we need to be that specific about how many electrons there are? Oops, I didn't clear this here. Why are there 8? So if I go back to the periodic table here, and I remove 2 electrons from... I got to find the periodic table. There it is. So here's calcium right here. I'm going to go remove 2 electrons. So that would mean I have 19 electrons, 18 electrons. So the number of electrons that are present would be the same as what argon looks like. In other words, I had 2 valence electrons on the outermost valence shell and valence shell 4. If I make it plus 2, I remove those 2, and now I'm back down to whatever the electron arrangement would be for argon. And argon is in group 18, so it has 8 valence electrons. Now, for our purposes, that's going to be relevant for us to remember is that, oh, if I make things have 0 valence electrons, it's the same as if they had 8. So later on, when we start trying to make things have 8, 0 is a valid option because going back to 0 resets it to 8 for the reason that we just saw here. So what I want you to do is I want you to figure out the number of valence electrons in each of these atoms or ions. And then find the valence shell that is present in them after you do the change, okay? Now, don't write any zeros for these because there will always be some number of electrons, okay? So I'll give you 5 minutes to do this, and we'll go over the answers together in just a moment. All right, how are we doing? If you got any answers, go ahead and type them in the chat here for me. I forgot that it was probably going to do that because these answers do look like spam. All right, let's go over the answers here. I'm going to cover up the chat very briefly here, just so I can have the periodic table on the screen, but also be writing. So we got arsenic, and you can see arsenic on here. I got to actually click on it here. Boop, there's arsenic right there. Arsenic is in column 15, so it's in group 15, which makes it have 5 valence electrons. And then what shell would it be in? Well, it's in row 4. So we would say it's valence shell 4. Can I just alt-tab here? Yeah. So I can... What's the next one? Boron. So boron is in group 13, so it'd have 3 valence electrons. And it's in row 2, so it's in shell 2. So remember, this is just what group it's in, and this is what period it's in. Now my parentheses look silly, so let me do that. Next we have carbon. Oops, that's not the pen. Carbon is in column 14, so that would mean it has 4 valence electrons. And it's also in period 2, so it's got shell 2. All right, now we get to the ions. So first let's find where fluorine is, and we'll mark it. So fluorine would have 7. But this ion here, this negative charge means that I add an additional electron. So it has 8 valence electrons. So let me actually write... I don't want you to think that because it's an ion, it's not a valence electron. So just trying to save space there. Now, we didn't add enough electrons to get pushed onto a new row, so we're still in shell 2. If I had added another electron, though, it would have gotten pushed to the next row. How about barium with a 3-? So where's barium? There it is, down here in the corner. So that is group 2, but I made it 3-, so I'm going to add 3 additional electrons. And barium's in row 6, so that's shell 6 here. Then we have potassium. I didn't select potassium. There we go. Potassium has 1 valence electron because it's in column 1. But I'm going to make it positively charged, which means I'm going to subtract that valence electron. So it has 0 valence electrons. And we said that if you have 0, that's like having 8, right? But that means that I go down to the previous shell. So I was in shell 4, but now I'm in shell 3. And then finally, xenon. Xenon is in group... Oops, I got to select it. Here's xenon over here. Xenon is in group 8, so it just has 8 valence electrons. And it is in period 5, so that means it's in shell 5. There you go. That's how you do it. And it looks like most people had most of those right. All right, we'll move this back out of the way. I almost grabbed the chat, and that would have been bad. I'd have to reformat that again. Boop, there we go. All right, so let me check my timer here. So we have a little bit more time before we do our break. So what we're going to do is we're going to apply that information. We have learned how to count valence electrons for any atom. Now what we're going to do is we're going to figure out what's the common configuration that we see in bonding. And it turns out there's a magic number. I wonder what that magic number could be. I don't know. But there's a reason for 8 being the magic number, and that's kind of the whole point of this discussion. So before we get to that discussion, we're going to learn how to draw all of the information that we just did as a picture. Because interpreting chemistry is not just a mathematical or linguistic sort of discussion. It's also symbolic. If we draw pictures of things, we can represent topics and concepts a lot easier than if we just try and write a sentence about it. So that's what we're going to do. We're going to rely on this guy's work. This is G.N. Lewis. G.N. Lewis devised a way to represent electrons around a given atom as a pictorial sort of diagram. And so you could see his work here. This is his journal. And what he was trying to do, I wish I could zoom in here, but I really can't. He drew a cube around an atom and started putting dots down. 1 dot per valence electron. And his theory was that, okay, if I fill in all the positions, all the corners of the cube, then I will get something that's stable. For example, sodium chloride here, he said, okay, well, sodium has 1, chlorine can fill the other 7, that'll be stable. That would explain why chlorine and sodium bond together so well. We're going to get to that in just a little bit and use his symbology, but we're not going to draw these cubes. Instead, we're just going to draw dots around something. And so this is called the Lewis symbol. So drawing a Lewis symbol is very easy. Step 1, draw the symbol. So that's the atomic symbol. So that'd be like oxygen is O, potassium would be K, calcium would be Ca, etc. Once you've drawn that symbol, you're going to draw dots on each of the sides of the symbol. There are 4 sides, up, down, left, and right. And each side can have up to 2 electrons. You're going to put 1 dot around each side per electron that you have. And then finally, as a formality, if you have an ion, you have to indicate the charge by putting the entire picture in brackets. So let's do an example here. So let's do the Lewis symbol for sodium. So step 1, draw the symbol. Boom. There you go. That's easy, right? Step 2, count how many valence electrons there are and put a dot around sodium for each valence electron. Well, if you go to periodic table, boop, and you find sodium on the periodic table, you'll notice that, oh, it only has one valence electron. So I should just draw one dot. Boop. There you go. That's it. It's not an ion. You're done. Now, for elements with more dots, you have more options, and so there's another nuance that we're going to follow. So first, let's do oxygen. Let's draw the symbol. There you go. Oxygen is just O. Then I have to draw a dot for each valence electron. On the periodic table, oxygen has 6 valence electrons because it's in group 6. There it is right there. So we're going to put 6 dots around oxygen. But remember that electrons repel. So the thing that we're going to do here is we're going to put 1 dot on each side, and then we'll start pairing them into pairs of 2. So do. Now I'm out of sides. My electrons have repelled each other as much as they can, so now I'll start pairing them. Do. And there you go. That's the answer. Now, a question that comes up is, well, what if I went the other way? I go counterclockwise or something like that when I'm drawing. What if I did oxygen and I went 1, 2, 3, 4, 5, I don't know, 6 or something like that? And so my unpaireds are on different sides than yours are. Is it still okay? And the answer is yes. You can have the unpaireds be on any sides that you want. So I could do this even, and that would be all right also. What would not be okay would be to do something like this. This is not okay. And the reason for that is I have this extra side here, and electrons repel. So one of my electrons would want to go to that side. They only pair up if they have no choice. So when you draw the Lewis symbol, you're going to have a certain number of paired electrons and a certain number of unpaired electrons for a given number of valence electrons. For 6, you'll always have 2 pairs of 2 and 2 individuals. And you can put those 2 individuals wherever you want to, on any side you want. You just cannot put them paired together, because they wouldn't be individual anymore. All right, so now what I want you to do, these are the same ions that you just had on the previous example. I want you to turn all of your answers that you just put in the chat into Lewis symbols. And when you've done that, type like I'm done in the chat or something like that so I know. Okay? I'll give you 3 minutes to do this. Then we'll draw out all the answers, and then we'll take a break. See you in a bit. Maya is super chatty today. All right, one more minute. All right, let's go over the answers. All right, so hopefully you remember where these elements were, so I don't have to keep like going back and forth with the periodic table here. I'm going doot 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 doot. So we remember that arsenic had. I'm going to count the valence electrons over here. So this is 5. So for arsenic, I would go 1, 2, 3, 4, 5, and I would put that pair wherever I want to, as long as I have 1 pair 2 and then 3 unpaireds. That would be correct for arsenic. Boron, we said, had 3. So there you go. You can put the 3 unpaireds on any side you want. You should have 3 unpaired sides and 1 blank side for boron. Carbon is one of the few that only has 1 way to draw it, and that's just 1 on each side. No other way around it. Fluoride here, fluorine with a minus charge, had 8 valence electrons. So when I draw this, we're going to put all 8 dots down. And then, because it's an ion, I have to put these square brackets around it and then indicate the charge. Same thing with barium here. So barium had 2, and then we added 3 more for this. So there were 5 total. So I'll go barium, 1, 2, 3, 4, 5. It's an ion. We'll put square brackets and indicate the charge here. For potassium here, potassium has 0, which we then turn into 8. Now, this is sort of where we deviate. So if you drew this and wrote this here, I can't really fault you for being right. But what we're going to do in this class instead, so we're instead going to draw, for anything that has 0, we want to keep in mind that it has 8. But what we're going to draw is we're just going to draw it blank with nothing. And the reason for that is because of how before, when I showed you the little Lewis structures in Gian Lewis's his lab notes, you're trying to get to 8, and we're going to be pairing potassium here with something like, say, fluorine that already has 8, and 8 plus 8 wouldn't be 8. 0 plus 8, however, is 8. And then finally for xenon, xenon just has 8. So for xenon, we would just do this. 1, 2, 3, 4, 5, 6, 7, 8. There you go. So aside from the oddity of what we do with 0, that should probably have been very straightforward. And now you can draw these symbols. My cursor is in the way, and it makes that look like there's extra dots there. All right, when we come back, we're going to talk about the octet rule. But we are due for a break, so I'm going to put... That's not the break time message up here. We're going to take a 10-minute break. I'll just keep playing some more Mega Man music, leave it on loop, and when we're done with our break, we'll get back to it, so see you in a bit. Alright, we are back. Let me kill the music here. Where is my periodic table? There it is. Alright. Okay, so for the second half of the class, we're going to apply this special rule to every atom and try and figure out how we make ionic bonds. It turns out that for certain elements on the periodic table, they don't react with anything very much. So, for example, xenon. Xenon's a noble gas. It doesn't really do anything. It just sits around. Krypton is also like that. Helium, argon, neon, they're all inert. They don't react. They're chemically stable. And the thing that they all have in common, with the exception of helium, because helium is tiny, is that they all have 8 valence electrons. And what we notice is that for various chemical species out there, the atom that has 8 valence electrons, or ion, compared to other forms it can adopt, tends to be more stable. So, for example, if I have chlorine gas looks like this. And if you breathe this, like, bad news. Don't do it. But if I give it an extra electron, let me do this in a different color here. I don't know why that one is a dash like that, but that's okay. If I do this, This is the primary component of table salt. So the difference between deadly and delicious is just an electron. Relatively speaking, this one is unstable because it is reactive. Chlorine gas is extremely reactive. It will oxidize your lungs very quickly, and you'll just basically not be able to breathe or absorb oxygen anymore because your lungs will be damaged. But this is stable and doesn't react. Which is why when you eat table salt, your tongue doesn't start violently fizzing with the water or moisture in your saliva or anything like that. So what we're going to do for all these ions is we're going to try and find the arrangement of electrons that leads us to get to the number 8. And so this is called the octet rule. If an atom has 8 electrons around it, and I should say an atom or an ion, because if you start with an atom and you add or change electrons, it'll become an ion. It will be more stable, and that's the octet rule. So our goal is to get to 8. We want to get to the magic number 8. Now, we're always going to try to get to 8 in the lowest number of steps possible, because nature is lazy. So if I have 5 valence electrons, I'm not going to lose 5. I'm going to gain 3 instead. If I have 7, I'm not going to lose 7. I'm going to gain 1 instead. If I have 1, I'm not going to gain 7. I'm going to lose 1. Okay. Remember that getting to 0 is like getting to 8, because then the previous layer becomes the octet. So our goal is going to be to look at any atom and tell me what ion it should form to be stable, because stability is getting an octet in the valence shell. Now, most of the atoms that we're going to look at won't have 8 valence electrons, so they're going to gain or lose electrons until they satisfy the octet rule. This means that there will always be one particular charge that is stable, and all the rest of them are unstable. That charge might be 0. In the case of noble gases, it is 0. 0 is the stable atom. If you made xenon with a plus charge, it'd be unstable. But for any other element in any other column, the ions are the more stable form. Alright, so let's do an example. Let's look at oxygen. Oxygen has 6 valence electrons, and I want it to be stable. So I need to give away electrons or take electrons, and I have to have 8 when I'm done with that process. So I want you to write in the chat what I'm going to do. Give or take, and then how many to get to 8. There you go. Give 2 to oxygen. Yeah, so oxygen will take 2 electrons from something. So there's my electrons. I'm gonna just say that I'm adding them because I'm putting them in a pool here. I'm going to take those 2 electrons and then go boop. There they go. Now, I didn't write the square brackets here because it kind of got a little bit crowded. But to be correct, we would put square brackets around this. Oh, there's my brackets. I forgot. It was a learning objective, I guess. Okay. All right, let's do another one. Here's calcium. What do I do with calcium to solve the issue of stability? Tell me what you give or take and how many. Now, if we take 6 electrons, that's a lot of electrons. You get to an octet, but is there a faster way to get to an octet? Remember how shells work, is my hint. Maya, what's the answer? She says, take how many? Very good, it's 2. I don't know why she meows in pairs of 2s there, but that's what Maya does. So I'm going to take 2 electrons away here. This is how I'm going to show that. And what I would draw would be, I don't draw any dots at all. But remember that the octet from the previous layer is implied here. So when you draw something with a 0 valence shell, remember that there are still 8 valence electrons. It's the previous valence shell that we were talking about that exists there. And so that's the option that we take. Getting rid of 2 electrons is much easier than taking 6 electrons for itself. And I'm mixing up give and take now, so hopefully in the context of what I'm talking about, that makes sense. So to summarize what we've seen on these previous 2 slides, elements are going to remove or collect extra electrons. And whatever option requires them to get to an octet in the fewest possible steps is the action that's going to occur. Now, what that means is that elements that are in the left side of the periodic table, so let's call the periodic table up here again. Elements that are on the left side over here have between 1 and 3 electrons. Now, I'm going to call this column right here the left side, even though it's more to the right. And so these atoms tend to give away their electrons so that they can become an octet by ditching 1 to 3 electrons. Elements over here on the right side have 5 to 7 electrons, and what they end up doing is collecting electrons. They gain electrons to get closer to 8. So metals on the left give up their electrons. Non-metals on the right tend to take electrons. There is one last thing to consider, though. What about elements in column 4? They have 4 valence electrons. They're equidistant. What do? And the answer to that is they sort of do whatever they want to, and there's an entire field of chemistry dedicated to that. Carbon is so weird that having 4 valence electrons gives it so many options that there's an entire year of chemistry that you get to study it for. If you are in biology or biochemical engineering or some sort of engineering that focuses on chemistry and materials, chemical engineering, for example, or even chemistry, you could take OChem. I personally think OChem is super cool, but a lot of people find it to be like scary. And I understand that because it's complicated. And I had the same mindset when I went into organic. And then I was like, wow, this is actually super awesome. So you might really enjoy it. Who knows? All right. So, what I want you to do is for these elements shown down at the bottom there, Cl, Ba, Ns, Prp, and Rb, I want you to use the octet rule to predict which ion forms for the following elements and draw its Lewis symbol for these right here. Okay? And then if you want to, you can count protons and electrons. That's sort of just an exercise. It's up to you. Then what I want you to do, down here, I have a series of ions that I have formed by adding and removing electrons. And what I want you to do is I want you to tell me, do you expect it to be stable? If it is, circle it, and if it's unstable, draw an X through it. Remember that stable means has an octet in the context of this problem. Okay? So go ahead and draw all these Lewis symbols once you have predicted the ions, and then circle and cross out stable and unstable ions. We'll go over the answers in about 5 minutes. How are we doing? 2 or 3 more minutes? Let me know when you're finished in the chat. All right, let's go over the answers here. I'm not going to have enough space to work on this page, so I'm going to go to this. And we'll do that. That crashed my window. Hold on. Create rectangle. That is not what I want to do. I want to just zoom in. There we go. Oh, I got to get rid of this layer window because it's right in front of my screen. Okay, so we got chlorine. And I have chlorine's in group 7, so it has 7 valence electrons. There they are. I want to get to an octet, so I need to give it an extra electron. So here's my extra electron. There's my charge on it. And there you go. Now, if you wanted to count protons and number of electrons, I'll just write those numbers down real quick. Barium is in column 2, and it has 2 valence electrons. What I'm going to do is, since it's easier for me to get rid of 2 than it is to take 6, I'm just going to go like that and go like that. That'll make this plus 2. Remember, we put the number first before the charge. I'm going to erase those to tidy up. And then if I count my protons, this is 56 and this is 54. Nitrogen's got 1, 2, 3, 4, 5, because it's in group 5A, or 15. In order to get it to an octet, I need to give it 3 more, because that's the easier way to do that, instead of getting rid of 5. And then I'll count protons, and I will count electrons. Sulfur is in group 16, or 6A, so I'm going to put 6 electrons down. To get to an octet, I will give it 2 more. There we go. And the number of protons is 16, and number of electrons will be 18. Where's phosphorus at? Phosphorus has 5... Oops, what am I doing? 5 electrons. I need to give it 3 more to get to an octet. There we go. And then rubidium here only has 1 valence electron. What we're going to do with that, we're going to take it away to make rubidium plus. We'll tidy up the structure to get rid of this. And then when I count my protons, it's 37 and then 36. There you go. So there are all of our valence structures. We have found the octet for every atom by either adding electrons to it or removing electrons to get to 8. We chose the closer of the 2 options, whichever took fewer steps. And then, now we got to go back and circle and draw an X through these. I can do that on this slide here. So, if I draw aluminum, aluminum would have 3 valence electrons. Making it positive 3 would get rid of those. Is that stable? Well, when I tidy up, there aren't any electrons there, which indicates an octet. So, this would be stable, and we'll keep it. How about selenium minus 2? So selenium has 6 valence electrons. If I make it minus 2 here, I would add 2. That's an octet, so this is stable. How about Br plus? So bromine has 7 valence electrons. But if I make it plus, that's the same as removing an electron. Is that a stable octet? That's farther from an octet. So this is not the ion that forms. We're going to cross it out. For calcium, calcium has 2 valence electrons. If I make it 2 plus, I get rid of them. That's an octet. That's stable. How about phosphorus? If I have phosphorus with 5 valence electrons here, and I cross out all 5, you might think, oh, wait a second, that's an octet. And it is an octet, but is it the easiest octet? An easier octet would be to have 5, and then add 3. So this is not the ion that forms. We'd instead get P3 minus, like we showed on the example above. Arsenic, same deal as selenium, really. Arsenic has 5 valence electrons. If I give it 3 to make it 3 minus, it now has an octet. And then cesium has 1 valence electron, but making it minus gives it another electron. That's unstable, so this is not what would form. You're going to see a question like this on the quiz that's going to ask you which ion is expected to form. Make sure that you are considering it from this approach. Tell me if the ion that is formed has an octet or not. All right, let me know if you have any questions. All right, now all of these rules, all of this octet stuff only works for elements in group 1 through 8A. So those, if you're using p-table, that would be groups 1 and 2, and then 13 through 18. For any other element, it doesn't work for the octet rule. What that means in terms of importance for us is that we can't use the octet rule to predict what ion forms for any other element. And so elements in the B group, so this would be groups 3 through 12. You can still make ions out of these atoms, but what charge is the preferred charge varies. It doesn't really follow the same rules. So what we're going to do is we're going to not draw Lewis symbols for anything in groups 3 through 12. We're not going to draw any B group Lewis symbols because the Lewis symbol rules sort of fall apart. Instead, what I will do is I will just tell you the ion or give you enough information that you can solve for it. So I might say iron with a 2+ charge, or I might say cesium with 3 electrons removed, or something like that. And so when we get to this section, which is going to be putting all of our atoms and ions together to make ionic compounds, I'm going to have to tell you to some degree how to do this when transition metals are involved, because transition metal complexes do form ionic compounds. But give me just a second. I want to see how much time, because we have 10 minutes left. I want to see how many more things I can cover in this section in 10 or 15 minutes. We can probably do a little bit of this. Okay, so let's keep going for a little bit. All right, so let's talk about how to make ionic bonds. First, we need to be a little more specific about what an ionic bond is. So we're going to define an ionic bond as any two ions that have opposite charges because they're going to be attracted to each other. So I have something that's positive and something that's negative. These two will be drawn together by some force. And that force is the ionic bond. Now, it's important to note that we're going to call the ionic bond this attraction specifically right here. But ions exert their charge in all directions. So if I had another positive ion over here, these two would interact, and then these two would interact, and so on and so forth, and all of the neighbors would interact with each other. But we're going to refer to the ionic bond as just the interaction between any pair. Now, what does this mean for the structure as we put all of these ions together? What ends up happening is that every sodium ion would attract neighboring chlorides. And then each of those chlorides would attract a sodium. And each of those sodiums would attract a chloride. And this pattern will repeat over and over and over and over and over for quintillions of atoms and ions. Like, there's so many. As this pattern repeats in all directions, you create what's called a lattice. A lattice is an ionic compound that is arranged in a repeating pattern from my ions that are coalescing together. So when an ionic bond forms, it keeps attracting other opposite charges to some extent. So in reality, yes, that's what happens because my lattice is just going to keep expanding in each direction pretty much forever. Because the sides over here, like this right here, has a positive charge, and any negative could go right up and go boop and just stick right to it. Kind of like magnets. You could make a really nice cube out of magnets, but you can always stick more magnets on there, right? Ions are exactly the same way. Now, when it comes to the formula of a compound, the formula is going to be whatever the simplest repeating unit is of that structure that is made. So not everything's going to make this regular cube. Some formulas are going to have like a magnesium and then 2 chlorines in it, because magnesium is twice as charged. So it attracts twice as many chlorines as there would be magnesiums in the structure. That repeating unit is called the formula unit because it tells you the formula of the compound. So it's important to note that when you're thinking about ionic compounds, they're not molecules. And it's for the reason that you just said there. When you make ionic bonds, you just keep making more ionic bonds to neighbors until you have created this giant lattice. But those ions will form a repeating pattern that makes the formula unit. And so we say that the formula of the compound is the formula of the formula unit. So when we look at the salt crystal really, really close, you would see that the formula unit is just 1 sodium per chloride. Because there is an equal number of both, and so you can find the repeating pattern very easily. All right. Now what I'm going to do is I'm going to show you how this actually occurs if you use neutral elements. So if I had like a bin full of sodium and a bin full of chloride, these ions, and I just poured them in together, yeah, you'd make a lattice out of it. But how does the actual reaction occur? What if I use neutral elements? So like elemental sodium, which is sodium metal, and then chlorine gas. Will those two things react with each other? And it turns out they totally do. So let me get this video up, and we'll watch this video, and then we'll probably call it a day here. Okay, is this Lonnie's lab? Yeah, this is Lonnie's lab. Okay. That's not what I wanted to capture. That captured live split. There's Lonnie's lab. Boop. All right. Lonnie is an instructor. I think he's at like UC Berkeley. Yeah. So what Lonnie's going to do here is he's going to actually make sodium chloride, table salt, from raw elements. So here we go. I'm going to talk over him, and I think that this is closed captioned. Yeah, we don't actually need the closed captioning. So here's what Lonnie's going to do. Lonnie is letting this tube fill with chlorine gas. If you look carefully here, you can actually see... Let me see if I can make it bigger here. If you look inside the tube, you can kind of see that where his lab coat is behind it, it's a little yellow, right? That yellow is the chlorine gas. Chlorine gas is very faintly yellow. Now I did that, I have to resize this again. Chlorine gas is very faintly yellow. It's super, super toxic, which is why he has it in this glass container on top of this like ventilation shaft. What this is this is just a very high power fan pulling air downward very quickly. So he's perfectly safe. That's why he's not wearing a mask or anything. When he removes the tube, a little chlorine gas does leak out because it is a gas, but that's fine. All right. We'll put the chlorine gas away for now. The next thing he's going to do is he's going to take sodium metal. Sodium metal is in this bin here because sodium reacts with water and it also reacts with water vapor in the air. It has to be stored under hexane or mineral oil. Mineral oil is unreactive towards sodium because it doesn't have any water in it. It's insoluble in water. He's putting it in another sample of fresh hexane to just kind of wash off all of the previous oil. Because hexane, the solution that he's using, is very volatile. And when he takes it out of that solution and then puts it in the fire, that hexane will burn off really quickly, which is why it'll turn orange the instant he puts it in there. So now what he's going to do is he's going to heat it. And the heat allows the reaction to progress much more quickly when he puts the sodium into the chlorine. This gives the electrons in the sodium the energy they need to bounce off the sodium and hop onto a chlorine atom. Now, very quickly, before we put this in here, you'll notice that there's a color here for the flame of sodium. When sodium burns, it burns a particular color. In this video, it actually looks a little more orange than it's supposed to. Sodium is supposed to be kind of a yellowy orange. And on the lab that you're going to do this week, you'll see that. All right, here we go. Here is the reaction of sodium and chlorine gas. Now, gas is being expelled from where he has the ladle in here, but you can see that it's just kind of getting sucked right into the vent. So he's not in harm's way. He still has a face shield on, of course. But as he moves the really hot sodium metal up and down this container, he'll find more chlorine gas to react with. And that chlorine will take the electrons from the sodium metal. Now, the white haze that's in here is gaseous sodium chloride. Eventually, those gas particles will be attracted to each other through intermolecular forces. By the way, this is how hot that got. That ladle is red hot. Now, if we let this sit long enough, this will make table salt. In fact, you can kind of see the table salt forming at the bottom here. Now, Lonnie prepared some earlier, but this is what it will look like at the end, and you can kind of see it down there. And so this is how all ionic compounds are formed, by doing this electron transfer. Now, how did all of the salt in our, like, say, ocean or, like, mines or something form? And, Lonnie, why are you eating in the lab? No, Lonnie, don't do it. Lonnie, this is not hygienic. You know there's a pandemic going on. And oh, goodness. Lonnie, Lonnie, Lonnie. Now, where did all the salt form that we have right now? All salt, all sodium chloride formed from that reaction that you just saw on the screen, but very, 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 very long ago. And when I say very long ago, what I mean is around the time of the Earth's formation. So, like, sodium atoms and chlorine atoms were created in a star, and when that star exploded, and then those two types of atoms ran into each other, they exchanged electrons to make salt. There was plenty of chlorine and plenty of sodium in this local region of space, and so we ended up with tons and tons and tons of salt. All right, so the process that just occurred here is called an electron transfer. An electron transfer involves the transfer of a valence electron from a metal to a non-metal, and that looks visually like this. I have sodium and I have chlorine. If I pass my electron over, I get two ions that satisfy the octet rule. And if I have satisfied octet rule, these will no longer react. They will not change the number of electrons they have. But as a result of this, they now have charges. Passing around electrons results in charges. And if you get charges, you then form an ionic bond. So that's where we are going with this discussion here. But that's really all the time that I have, because the next section is just going to have us do a bunch of examples, and we won't have time for them. So I'm going to hit stop here for today. We'll go to the title card, and we'll talk a little bit about next week. So next week, we're going to finish up Chapter 9. We'll probably start Chapter 10. Your lab worksheet number 3 is due on Thursday. And I was going to talk about the Monday holiday, but the Monday holiday doesn't really apply for this class because we don't have class on Monday. So enjoy your Monday and enjoy all of the crazy snow that's apparently supposed to fall out here. Like, I'm looking at the weather and they're calling for 5 inches of snow or something like that. So stay safe and warm, but go play in the snow if that's your thing. It's not mine. I hate snow. I'm going to stay where it's nice and warm.